I'm doing some reverse engineering. I want to interface into this unit here and get the data out of it and transmit it onto my own network and actually import that data into a web page. So I'm reverse engineering this a little bit and figuring out its protocols, and I thought I'd just show you what I'm doing. So to give you some information about what's actually going on here, this is a timer interface, right? This is used for various sports and activities. It's basically a timer display. I'll flick it on. It will display a time. If I do a manual stop and start, okay, it's working. Okay, it has light curtains which are used at the start and stop points of the course, and it sends signals to this unit, hence the antenna, which it then turns into a time. And it's got all sorts of functions built into it, but basically most of those are not used in this particular application. I just want to capture the time out of this and transport it into something else. But I had to reverse engineer its UART protocols, because it does have an output on here. It's got input, output and audio. There's no documentation about the output information, that sort of stuff. There's just no information I could be able to find, at least. So I've had to reverse engineer what it's doing on the output here. It's nice to have got an output, because that's for their own accessories. They sell accessories and go with it, such as a big LED display sign and stuff like that. So I originally started out using this Arduino Pro Micro over here. I was using that originally. I was interfacing to this. Now that was all fine and working nicely until I wanted to put on a MicroSD card reader, because I want to dump the data onto an SD card. So I want to do two things. I want to dump it onto an SD card as a backup, and also I want to send it across a network as well to be recorded by a computer. Those are the two things I'm trying to achieve. It was okay until I went to do this. So the problem I had is that the MicroSD card, the libraries for this, caused me to run out of memory on the Pro Micro. So damn, this kind of ruins that, because I want to back up onto an SD card. It's quite important. It's got a backup as well as going through the network. In case there's a network failure, for example, at least then it won't cripple the system. Obviously you could write to internal EEPROM, but yeah, I don't really like to do that, because then you have to actually plug into this thing to try and read it back or something. Or maybe I'll have to do some other thing, but I want to do SD card. That way I can just unplug the card and plug it into a computer and get the data off. Right, nice and simple. Don't have to mess around at all. So I ran out of memory, and that was a bit of a problem. I had to change over to using an ESP8266 because I happen to have one laying around. So you can see the mess of wiring here. I had to use this instead. So I've got a little OLED display here. This is just a testing one. I will be changing this to a much larger display. It needs to be quite large so people with bad eyesight can read it, because right now I can read it, but not everyone can. That uses these things are usually older people, and they tend to have eyesight issues and forget their glasses, that kind of thing. Believe me, it happens. The memory size on this is much bigger than the Arduino Pro Micro. Okay, so much larger. So I'm not running out of memory space on this, so I can run the display. And it's also got Wi-Fi built in as well, being an ESP8266. And I'm also want to interface this with a LoRa module as well. Now the only concern I've got now is I'm thinking, well, I'm running out of inputs and outputs, so I may have to use expanders as well. I don't really want to go there, but I may have to do something like that. But it works. It's doing what it's supposed to do at the moment. Now the other thing you might notice is this little circuit up top here. I'll scope it in a minute and I'll show you what I'm doing. But this circuit here, it's kind of messy, but you know, it's actually a level converter and inverter. Okay, this is basically a single transistor and a couple of resistors. Okay, so what I'm doing, because the protocols that come out of this device are not true UART, it's using an idle low state instead of an idle high state. Now on a scope it doesn't matter, because you can just change the state and it will just decode it. It's absolutely fine, so you'll be able to see that on a scope shortly. For this device here, or the Arduino, they require a idle high state in order to be able to decode using the standard protocols, right, without having to rewrite stuff. There's probably some way of doing it. It's easier to chuck a transistor and a couple of resistors in. That's to say, it does dual function. One is it's inverting the signal, and the second function it's also level shifting, because it's only one-way communication. Anyway, it's only out of the device into these. These are only reading it, so it's a TX line coming in. What is coming in though, it's over 5 volts coming in. Now the Arduino would be fine with that, you know, it's only just over 5 volts, but the ESP8266 is only 3.3 volts, and you to put 5 volts into that, you're going to damage it. Using this level converter setup, that means this is safe as well, so I'm going to change the voltage level going to this level converter. Even mind you, the Arduino will read 3.3 volts just fine, so I'm not too worried about that, but you can actually read it. It still treats it as a high state, so it works. What I've got here is a 3.3 volt line coming over, so we have this little jumper block on the back here, 2-pin header, and the back comes in. That's the signals coming from the box. So you've got a resistor here, which is in series with the output from that device. Okay, that's a current dropping, voltage dropping resistor. That feeds the base of the transistor. It's a bit hard to see, I'm afraid. That's feeding the base, which is the middle pin. It's a 2N 3904 transistor I'm using here. Just off the shelf, just standard thing, nothing particularly complicated about that. And the ground side, because it's battery powered, it doesn't really matter, so ground side's coming down, so it's common grounded all together. You need it anyway, probably. This wire here is going to my Scope Pro, ignore that. This wire link is just to get a bridge it across here, so it's not actually used. So you've got the ground there, or 0 volt rail, going straight down to the ESP8266 or Arduino, whichever one you're using. Then obviously to the emitter of the transistor. It's pin out as emitter base collector. Now that's that part of it. Now the pull up side is done from the 3.3 volt rail in this case, from here through this resistor to the collector of that transistor, which then also comes out to the RX line of the ESP8266 down here. So that's the actual serial connection is through this wire. Effectively, when there's a high state coming in, it calls it to give a low state coming out, and vice versa. When it turns off, the voltage is pulled high by that resistor there, that pulls the voltage up, which obviously then inverts it and makes sure the high voltage is not 5 volts but 3.3 volts, or slightly lower because of the resistor. Okay, so that means it's all perfectly safe for the ESP8266. You can buy level converter transistors or ICs or whatever. You can buy those devices quite easy, they're pretty cheap. Level shifters, which actually go bi-directional as well. But in this case, I didn't require that, and it's just easy parts, you know, a couple of cents worth of parts, not really worth worrying about anything, you know. So that works fine. Now I'm going to scope probe it. Well, I've already got a probe in there, but I'll scope it and I'll show you what signals we're getting and what I've discovered so far. Right, so let's show you this. Now I've got this set up already with decoding, everything already set up. By default, there's actually have different baud rates settings inside them. You have to go into like a hidden menu system to get to that, but I've found it. It's got different baud rates and different configurations for the kind of output that it will spit out. And because of that, it's actually a bit tricky to deal with because it's got different functions, and depending on what those settings are, it can influence the decoding system. It was by default 1200 baud. I've changed it now to 4800 baud just because I want the data to come through a little bit faster. It can actually get higher than that if this is used for other functions as well. So maybe they're running a cable out to a display, maybe they need to have a bit more noise immunity, that sort of thing. Having a higher baud rate can cause problems with that, so that's probably why it's default very low baud rate. So if I look at the bus settings, so I'm using just analog bus because it's using the channel 1 input. Your hex or binary base for that, yeah, whatever. Let's trigger it and actually show a signal, shall we? Now I've got a 1 volt per division setting, and we're also 1 millisecond per division. So I've got it set on single capture, so let's push a button, do a start, and there's the initial pulse. Now that's all it puts out when you start the timer. Okay, when the timer first starts, that's all it puts out, which is translated into a carriage return, or decimal 13. Okay, if you're doing an ASCII, this is actually doing ASCII decoding at the moment. But this particular scope will actually convert those into the special characters. So if it knows a special character, which is decimal 13 is a carriage return, it tells you it's a carriage return rather than just leaving it blank. Some scopes will not do that. They'll actually just have a blank section and you actually know what it's actually sending. You have to go into decimal decoding and get the decimal numbers out of that instead, or binary, or maybe hex, whatever. But as we're doing a UART and it's basically text coming through, then you know that it's a carriage return. So that's the first pulse that comes out of it. I'm going to make this a bit narrower, so we catch the next pulse because it's much bigger. Do a single capture and we'll stop it. That's what it does when it stops. And over here, again, you've got the same thing. You've got some invisible characters, special characters, which are sent through, which on some scopes would not show up at all. So again, we've got some invisible characters here, and the scope has recognised that those are non-standard ASCII characters, or they're non-printable ASCII characters, I should say, and it's actually told you what they are. I already know what these are because I've done decoding from decimal, but SO is shift out, SI is shift in, SP is space. Alright, so it's telling you what those characters are, which is really nice. And then we have this readout here. Now what it's basically got, this display, has a 3-digit output before the decimal point and a 3-digit output after the decimal point. And so what it does, it uses spaces as fillers. So it's got a space, and then you've got the time there, which is 61.654, which is coming up in this case. Alright, that's what the actual time is. Then it's got another space, and it's got brackets and the M. And then it's got a carriage return on the end, just like the start point. So it's got a carriage return for start, carriage return for end. So that's that bit there. So I'm having to decode this. As you can see, it's idle low state at that point from the device. So if I bring this down some more, do another single capture. Now I'll do a start really quickly. There we go. You can see that if I do it, that's a start point. That's when I've started the timer. That's when I stop the timer. But there's also a third pulse over here. Alright, so let's have a look at that one. And this one is a little bit different. It starts with spaces, goes space, space, space. Then it's got some text. It says time, space, false. Space, then another time. Okay, so these are part of the calculations the unit can do. can output time faults based on the settings that have been preset into it. So if it's set to do, say if it's set for 60 seconds, and if you go over 60 seconds, it will give you a preset amount of time faults depending on how far over that you are. So per second it will give you a fault, and it will display that on here, so you can actually spew that out. So this does the calculations for you. Yeah, I mean, yeah, I'm doing that in software anyway, so it doesn't matter. I don't actually need that function. So that packet there I don't actually need. So I actually need the first two packets to start. I don't even need that one actually, to be honest. All I actually need is this packet here, the middle one. So all I'm trying to get out of it is the time. So when it spits this out, I know, right, it's done, and I can move on. Now there is also a different packet, so I'm going to show you that one. This, yeah, it should be good enough there. Actually, I might need to get an error. Right, do another single capture. I'll do restart pulse. Okay, there we go. So now we've got a different packet here. So what can happen is this has actually got the ability to detect if there's like a fault, and you can push a restart button. Like so, you got the time will stop. So if the time stopped, but you realise, oh no, it's been falsely triggered by, say, a fly flying through the light curtains online, for example. You can push the restart button; it will restarts the timer. Alright, so I'll do it on here. There it starts, carries on from where it left off. Okay, so it's still counting in the background. And what it will output is this instead. So you've got upper arrow, everything, space, and this is restart. Oh, use the right control. Restart, hyphen, ignore, space, time, space, upper arrow, carriage return. So it's using carriage return as the end of the line, effectively. And then we've got this other packet there and there. So let's bring these over. And then there's that same one as before, exactly the same packet, gives you the time. And then there's another packet over here, which is the time faults one. So it's exactly the same, it just prefixes the original output with that restart statement. That's what I've been reverse engineering and putting onto here. Right, so as I said before, this is a inverted display, so I'm going to show you the output level of this. So as you can see on here, that's 5.1 volts peak to peak. You can probably just see it. Yeah, right, 5.1 volts. So that's the level coming out of that device. Now if I reprobe somewhere else, like right here instead, just put that in there, I'll do another single capture. Okay, so let's done a single capture here. Now this is after the resistor going into the base of the transistor. So you can see the voltage here is 1.13 volts peak to peak going into the transistor. So it might be overdriving it very slightly, but it's only little pulses, so it should be fine, I think. At least we know we've got a nice solid on state. It's not going to be in its linear region, it's going to be, you know, latched basically. So that's fine. Then we come over to the next pin over, and that's the output from the transistor, which is that serial going to the ESP8266. So doing a capture on that, this level should be about 3.3 volts. There you go, start stop pulse. We get 3.7 volts peak to peak, which is interesting. So it says 3.3 here. That's what I was measuring, 3.3 volts, because it's in its high state. So it'll be pulling down to ground, it won't be going below ground. Mind you, I'm shunting across with a transistor, so maybe it will be producing something slightly lower. There's no inductance, well, there is inductance in the cables and in that small section there. Inductance was what caused it to work, so if I explain it better, try and string a train of thought together. And a buck converter or a boost converter uses inductance to affect the voltages, okay? So in the boost converter, for example, it will shunt across the inductor, which causes a current spike, and then when it unshorts, it boosts it up, it causes a voltage increase. And you can get a similar effect when you're switching across the supply with a transistor. Again, you know, that's basically how they work. So I'm getting a slightly different voltage here, but it's going to, you know, 3.7 volt peak to peak, but it's reading 3.3 volts on the actual supply rail, because I say it's normally high. So right now it'd be a high state, which is why it's reading 3.3 volts here. So that's the actual output which is going to this. So that, you can see that conversion box there is going from 5 volts down to 3.3 volts to supply the ESP8266. It should all be fine, really. Okay, if you look at the display just here, you can see I've got some. The dog number thing is preset. It's just like a holding number, and the middle line there is the time, which it's getting from the timer, and here are the inputs. So these are counting up inputs, alright? They're not currently configured or connected up. If you change the state of one of these inputs, it will count each one. So this one will just count up indefinitely. Each time you hit it, it will count up. Middle one will only count up 3 times, and then one will only count up once, because they have different functions. They're part of the scoring system. So the idea here is we're going to basically building a controller which takes the time, takes these what are called faults as part of the run, collates them all together, and then sends that through to the web page automatically as soon as the time's completed. So that's the plan of it. So if I turn the time back on, I currently turned it off because I save batteries. So I'll turn the thing on and we'll start the timer. So it says running, it means the timer is currently counting. At that point you can actually still put information in here for these faults, things like that. You can enter those with buttons as it's counting. Then once it's finished, it will display the time on here as well as a confirmation that you got the time okay, and then you can do it, enter button, it will send it off, and that's what the plan is. But that's all part of it. I've got a lot more of the development to do on this yet. This is just the initial stages of the user interface section of it, basically. And I've got to build the Wi-Fi. So I have 2 networks. I use Wi-Fi and LoRa. But as I'm only sending text data in little packets, you know, every maybe 30 seconds or so, maybe longer, it probably shouldn't really matter that much. Yeah, we'll see how that goes. I haven't tried LoRa before. I've never used LoRa, but this is part of what I want to do. I need a longer range, because if the Wi-Fi doesn't reach, I need something which is longer range, which will also send the data in a similar method. So if I'm using Wi-Fi, I can go straight to the web page, and LoRa can probably just interface through something else. So we'll see how we go. So a continuation of this project. I built a prototype. This has actually been used at an event. This was a different display, the little original one I had on there before, the 0.96 inch, and it actually worked. I had a few little bugs in the code which I've since fixed. And I've spent a lot of time in the code. I've got like 3,500 lines of code just on this thing to allow for various circumstances and various situations, so it will deal with them eloquently rather than crashing or doing something weird. So it's been a lot of complication trying to deal with that stuff, right? So yes, it does work. So it saves to SD card, it sends it over Wi-Fi, and it also sends it over LoRa. Excellent. So here's the inside there. Now the LoRa module is currently not plugged in. I've been doing something else, so I'll be reprogramming it, so I've unplugged it. So it's not there right now, but there's the SD card, obviously the Wi-Fi is built into it. And the LoRa module is usually just like tucked in. But I've only done the LoRa module during testing. At the time at the event, I didn't actually have the LoRa modules, didn't arrive in time. So I used Wi-Fi at the event, and that worked fine. I uploaded it straight to the website, bang, you know, submit the result, is on the website. So that part's all working really nicely. So I've done a lot of work on this, it's been a few weeks now. So if I just chuck a time into it, and there we go, it's got a time. Should be the same time as on here. And these buttons are working. You can see it's got some extra buttons on there. Before I had 6 buttons, now I've got, there's actually one missing off here, there's one more button it needs. So it's a lot of buttons on there, more buttons I really wanted, but all of them are necessary. So I'll submit that. Next one. So you go to previous results, next results, or the queue, and you can go back to a result and you actually edit it and resubmit it, and it will send it again. And you go back and that says it's been edited. That's what the E means. So stuff like that. That's all working fine. Dog number. When I at the event, I was actually had this plugged into my my MacBook, and I was sending the dog number over the serial connection through the USB. So I was manually typing it into the computer, which is dumping it onto the ESP32. And then that's how I was actually doing it dog by dog, so that worked fine. Project's been going really well. I've ordered a board because of the size of this board here, and my restriction Eagle only being able to do was 80 by 100mm or something like that. I've had to do this in 2 boards, so I've got one board which has all the buttons on it, well, those 9 buttons on it. And I've got another board which is going to be a controller, so that's got the display, the ESP32, the LoRa, the SD card, and stuff like that on it. 2 more buttons have to go on here. They're actually got to be wired onto the bottom panel. So I'm not quite sure I'm going to do those yet. I've still got to figure that bit out. It's a bit tight. So I'll probably get those boards made and figure out from then. So that's that part of the project. That's in progress. That's going really well. And the boards are ordered. I'm just waiting for them. Probably be another week or so before they can turn up. That's all good. That's working. I'm happy with that. Now on top of this particular part of the project, I've had to do a few bits. Now another thing I have to do is an interface for LoRa for the other end of this. Obviously I'm sending data through LoRa. If I've got a Wi-Fi connection, it's fine. It doesn't matter. But I'm expecting to use this at ranges where Wi-Fi won't reach. So that's what the LoRa's for. I need a LoRa interface to receive the LoRa signals and convert that onto my Wi-Fi network and then send it to the website. So it's an intermediate gateway. Now I've already built that. I'm going to do it in a separate video. So thanks for watching this one. I'll update this when I get the boards, and I'll do a proper video on that. And you'll see me building the boards and actually getting the thing working and testing it and that sort of stuff. I'll do a video on that. So if you're interested in seeing me get this thing up and going properly with a proper PCB, which is being supplied by PCB Way at no charge, by the way, then make sure you check out those videos. It's going to be quite interesting. So Wi-Fi, LoRa, SD card, ESP32, OLED display, awesome project. And that's just one part of it. It's got a few parts to it. So this is just one part. And I'm going to do another part of it in another video. So I obviously got one for that PCB and getting that going properly made. And I've got another project which is probably going to be more suitable for most people. I'm going to give a sneak peek now, because I'm going to do a video on this. Ignore the mess of the board, but it's basically ESP32. We have an OLED display and a LoRa module. And this is my LoRa to Wi-Fi gateway. So I'm going to do a video on that shortly. So make sure you subscribe and check that out too. Thanks for watching. Catch you later. Bye.